Okay, we can start. So, welcome everybody in person and online to this course, Science of Storms. I would like to thank Professor Djordje for inviting me to Genoa to teach this course. It's always my favorite city to visit. I've been here several times and I hope to be here many more times in the future. So this course is 12 hours, 6 2 hours lectures. Yes, Carol. So each lecture will start 15 minutes after the full hour and then run up to next full hour, and then we have 15 minutes break, and then that's the second hour. So it's really not 2 hours, it's a little bit less. So lectures will be also broadcasted here on Zoom and recorded, and these recordings can be shared with you if you request, if you send us email that you would like to have access to recordings. Recording, you will not be able to download recordings, but you will be able to watch them online. In terms of the evaluation, there will be final exam and nothing else. Together, Professor Burlando and I will quiz you. There will be 2 questions that you will do. So there, at the end of every lecture, I'll give you a list of exam questions associated with that lecture, and you will randomly pick 2 questions from a pool, and then you will answer them. Okay? You will have some time. I don't know what is the standard, so a little bit prepare your concepts and then answer the questions. So there is no assignments, there is nothing like that. Also, after every lecture, I will give you a literature that you can read that is associated with what I taught. To be honest with you, I actually forgot to put that in today's slides, but the version of slides that I will send you will contain that. I will share my slides with you, but as you will see today, there is nothing in slides. So you are basically left with literature that I will suggest and taking your notes. And well, actually notes, literature, and then you can always ask me questions. Either I'm staying in Professor Burlando's office together with him, so you can visit me there or send me email, okay? And my email is in syllabus. I don't know, did I skip anything? Are there any questions about course format or what I just said? You can always interrupt me and ask questions. I will ask you some questions, so don't be shy. There is no points for being wrong here, so you can just go wild and be wrong. For people online, maybe actually, so I will, how do I do this? So I enabled audio, but please make sure your microphones are off. And then if you have a question or you want to say something, then say something. But don't just keep your microphone on. So also something I want to clarify, yes. So the course is Science of Storms. Many of you do research, I believe, in wind engineering and extreme winds, but this course is not just about extreme winds. So it will be many other natural hazards like hail, flooding. I don't know, maybe I will even talk about UV radiation and so on. And so as you saw in syllabus, every lecture is pretty much different storm or something like that. Except for the first lecture today, which is more fundamental, and the most difficult lecture to put together for me. Because I'm supposed to explain entire atmospheric sciences in 2 hours, and then we have background to study different storms. So today's lecture will be very, very high level overview, and I'm skipping many, not even details, many topics that we could delve into, okay? So as you saw, today's lecture is on wind and convection. But really, I'm going to talk a little bit more about many other things. So the first 45 minutes will be kind of wind or dynamics. The second 45 minutes will be thermodynamics and stability and convection, okay? So we can start by defining air, and air is a mixture of gases. Approximately 78% is nitrogen, 21% is oxygen, and then 1% are other gases. And out of these other gases, it's really mostly argon. And then water vapor is very variable. It can be between 1 and 4%. It can be between 0 and 4%. And then CO2 and so on. This is what we breathe on a daily basis. And this is how our atmosphere was for thousands, millions of years now, pretty stable. Now, as I said, atmosphere is a mixture of gases that is different compared to compounds. Mixture means you have a bunch of, well, these are molecules, but we could really say atoms or molecules. They come together, but they do not lose their original property. Whereas in compounds like salt, what is salt? Sodium chloride. Both sodium and chloride are not good to eat, but when you combine them, they lose that property and you eat salt every day, no problems. Atmosphere is not like that, it's a mixture, okay, of these gases. And if we look into the atmosphere, if this is the surface of the Earth, I will use Z as the vertical coordinate. Of course, there is gravity. So if you could visualize, I mean, molecule atoms are 10 to negative 10 meters. So you cannot, of course, see them even anyway. But if you can visualize, then there is really a lot of them close to the surface. And then as we are moving away from the surface, there is less and less. And that's, of course, because there is gravity acting down, compressing the air to be close to the surface. So if we would look into density of air, how density of air changes with height. If I make this now, here is density, we use rho, you will see that density of air is pretty much exponentially decreasing with the height. The sole reason is that there is gravity that pushes air together, but it cannot completely compress it because there is also resistance of air. Now, that resistance of air is, of course, quantified with the pressure gradient force. We will talk a little bit more later in this lecture. Okay? Now, surface value of density at sea level is approximately 1.255 kilograms per cubic meter. So you might ask yourself a question. So if you take a volume of air and you measure percentages, you will always get this. You go here, you go to Canada, you climb 100 meters. There is always 78% nitrogen, 21% oxygen. Now, if you are at a certain height, of course, there is less air, like at Mount Everest, density of air is smaller, but these percentages are still satisfied. Now, they are satisfied up to certain height. Anybody knows that height? That height is up to about 100 kilometers. So we could split the atmosphere, if this is the surface of the Earth, we can split the atmosphere into two regions. One is called homosphere. What is homosphere? Homosphere is part of the atmosphere where these percentages are satisfied. And that is approximately 100 kilometers in the first, 100, 120, there is no fixed limit, but about 100 kilometers above the surface. And then above is heterosphere. Heterosphere. Now, there, in heterosphere, these percentages are no longer satisfied, and you mostly have light gases like helium, oxygen, but in atomic form, not in molecular form, hydrogen, and so on. But all weather and processes at the surface are in homosphere. So we are really, at least from the point of view of this course, we are not interested in heterosphere. Any questions? Now, the other thing about the air is that when we talk about air, we say that air is fluid. But really, what I said here is, I mean, in principle, it's bunch of particles over there. So fluid is a continuum. That means you can cut it as many times as you want. You still have fluid, or you can add more fluid to it, and so on. It never, you cannot. When you accept the assumption of fluid, that means you can cut that fluid as many times as you want. You will never end up with particles. But that's clearly not the case because air is made up of particles. So how do we conceptualize the concept of fluid? So if I take, now if you zoom in somehow in your mind at these molecules of air, and I take this many of them, okay? And now I want to calculate again this density that I discussed there. Density is mass over some volume. So let's say in 3 dimensions, of course. I take this volume and I calculate mass of these. Mass, and then I calculate density here. And here, this size of this rectangle is L. So I will put L over here. So for given L, for given volume of this cube, I will get some density, let's say here. Now I increase L. Okay? I will get some other density. I increase it even more. In other words, I'm increasing this cube, I will get some other density. So I keep doing that, I will end up with something like this. Okay? So there is a critical size of the cube for which your properties of air, in this case density, become independent of the container that you use to analyze it. Okay? Here, this is now a concept of continuum. Okay? Here you are not in continuum, you are in statistical theory of statistical mechanics, okay, kinetic theory of gases and whatnot. But here you are in the concept of continuum. Now, generally, how big should this cube be? This cube should be at least psi, should be at least 10 values of the mean free path of molecules. And mean free path is average distance that atoms traverse before hitting an atom, which is 10 to negative 7 meters or so. So you can see that very, very small volumes, you're already in the concept of continuum. That's why when we study anything, we don't care that there are atoms, that hydrogen is a little bit different than this. We don't care about these things, because our volumes are so big that this is satisfied, okay? This concept is the same if I'm measuring average height. I take you, your height. She's, let's say, much shorter than you. I get some different number. But after 100 people, it really doesn't matter who is 100 first. The statistics of the first 100 is so heavy that you don't get too big fluctuations. The same is here, okay? Okay, so I say this because we are generally not going to talk about molecules and atoms in this course. So from the point of view of then atmospheric sciences, we talk about air. So yes, we don't talk about whole atmosphere. Now, okay, let's analyze something and I say, okay, the whole atmosphere is such and such. That's not what we do. We define things that are called parcels of air. Parcel of air parcel. Air parcel is some imaginary volume of any shape. You adjust shape for your particular problem and research. And then we look into how this air parcel is different to the surrounding, to the rest of the atmosphere. Is it warmer? Is it more humid? Is it more faster? And so on. So that's the concept. And again, this parts of the pair is bunch of molecules and atoms, but we don't care about it because we are in the concept of continuum. Okay? Okay. Now, how do we explain dynamics of this particle pair? So let's say here is the surface of the Earth. In this course, I will use Z to be up. I will use X to be one horizontal axis, positive towards east. I will use Y to be other coordinate axis, positive towards north, and Z is positive up. So when I cross X, Y, I get Z. So anybody knows equations that would describe motion of an air parcel? So this air parcel is moving like that. What would be equations that govern the motion of this air parcel? Well, actually, it would be the greatest law ever, in my humble opinion, the greatest law ever discovered in the history of our species, and that is second Newton's law. Mass times acceleration is the sum of all forces. Now, here is a big, well, I don't know big, but the difference between classical engineering and atmospheric sciences. In engineering, generally, you have a law in this form because you made a deal with this desk, and I can now, you just tell me that give me mass of this desk. I weigh this desk or this remote, and then you study whatever is happening. In other words, it's not that difficult to determine mass of some object. But in atmospheric sciences, if I tell you this parcel of air over here, first of all, where is it? Second of all, how do you measure mass? And third of all, there is constantly interaction. This parcel of air is not always the same parcel. There are molecules coming out and away. There is energy coming in form of radiation. So really, we define this law that acceleration is the sum of all forces per mass. So we look into forces per mass rather than in this form over here. So all forces that are derived in atmospheric sciences are given per unit mass. Generally, unit mass is 1 kilogram, but in principle, it doesn't have to be 1 kilogram. So if I would write this law, let's say in the x direction, so I would get also the velocity vector in atmospheric sciences is such that u is associated with x direction. This is just convention. V is associated with y direction, so positive towards the north, and W is associated with z direction, positive up. So if I would write this law in the x direction, I would get du dt acceleration is equal sum of all forces per unit mass. Do you know some forces that are of importance in atmospheric sciences? I mean, in atmospheric sciences. For the motion of air. Gravity, U. That's correct in principle, but incorrect in terms of the x direction. Because x direction is horizontal, so gravity is not important. Gravity is in the z direction. Any other force? Pressure difference. Yes, so it would be pressure gradient force in the x direction. Any other force? When I teach some other courses, we derive all these forces, but there's no way we can do that today. So I will just, so pressure gradient force, any other force that crosses your mind. Coriolis force in the x direction, any other force that crosses your mind. viscosity in the x direction. Okay, so these are generally the forces. Air is electrically neutral, so there are no electrical forces that are of importance here. Now, in terms of equations, pressure gradient force in the x direction is 1 over rho. Rho is air density. Delta P, delta X, pressure gradient, what this gentleman said, pressure difference, plus Coriolis force in the x direction is F times V. I will soon tell you what is F. And plus viscosity in the x direction is nabla square times U times ni. This is kinematic viscosity of air. U is velocity in the x direction. F is Coriolis parameter. F is 2 times omega. Omega is angular velocity of the Earth. 2 pi over 1 day times sine of P, where P is latitude. Now, if you get this question in your exam, I will not expect you to know these equations because I'm not deriving them. If I was deriving them, I would ask you to know it. But what I will ask you to know is at least to write them in terms of letters, so you know the forces that are of importance. So, do you know the action of the pressure gradient force? How does this force act?
In terms of widths.
In terms of, if you have a parcel of air over here, in which direction will this parcel of air move thanks to the pressure gradient force? How?
From high pressure.
So yes. So this is pressure gradient force always acts from high pressure to low pressure. It tends to equalize pressures. Coriolis force is a tricky force. There are books, actually, I read a book on the Coriolis force. It's a quite nasty force. But in principle, it's a consequence of Earth's rotation. And in the northern hemisphere, this force always deflects motion to the right. In the southern hemisphere to the left. Okay? And the force is, as you can see, proportional to the angular velocity of the Earth, but this is constant. Latitude. So the further you are from the equator, the stronger the Coriolis force. Or at the equator, there is no Coriolis force. This is the reason why hurricanes never, absolutely ever, form at the equator. Because they need at least a little bit of the Coriolis force, and there is no Coriolis force at the equator. And this force is also proportional to the velocity. And viscosity, this is kinematic viscosity, about 10 to negative 5 meters squared per second. U is just velocity. And then dV dt would be negative 1 over rho delta P delta Y minus F times U plus mu nabla square V. Okay, so again, pressure gradient force, Coriolis force, viscosity. I always, you see, these are, I mean, I did this a million times, so I know it by my heart. But the question could be, how do you remember that here is plus and here is minus? Did I just check this before today's lecture? I mean, I did, but there is a better way to know. Okay, there is a better way to do it. How do you remember that here is plus, here is minus? Based on what I just told you about the Coriolis force. Look at this. This is my discovery. I'm going to publish it as a paper. Look at this. You are in the northern hemisphere. This is how I would remember. You are in the northern hemisphere, and you have velocity that is positive towards the north. So that would be like this V. And we said Coriolis force is turning everything to the right. So this V will tend to become U. thanks to the Coriolis force. But positive U is towards the east. This is north. So I know that Coriolis force needs to be positive because it will positively contribute to this U. Whereas in the second equation, if I have motion from west to east, then that motion, northern hemisphere, Coriolis force will be deflected to the right. And to the right is south. And I know that south is negative y direction, so I know that this needs to contribute negatively to my v. I don't know if this is the easy way to remember it, but that's how I do it, okay? And then lastly, we have dw dt, which is minus 1 over rho delta p delta z minus g, gravity that you said, and again, viscosity, okay? We only have 5 minutes, but I cannot resist not to ask you this. You see, we always talk about turbulence, and there is no turbulence force. So where is turbulence in all this business? Josip online is constantly parameterizing turbulence. Well, where is turbulence? There is no turbulence, and we yet say turbulence is a force doing something.
It's in the velocity.
It's in the velocity, because, for example, du dt is delta u delta t plus u delta x plus v delta u delta y plus w delta. And these are actually the terms that are nasty. These are nonlinear terms. Function is multiplying its derivative. Turbulence is still not here, but it's hidden. And you get it once you, which we will not do here. But most of you heard that you can decompose instantaneous velocity as the sum of average plus perturbations. And then these perturbations end up being associated with turbulence. And indeed, then turbulence ends up being an additional force. Yes.
I have a question about this. You have to make the assumption that the flow is stationary to do something like this.
Yes.
But otherwise, it's not like this.
Yes, that's correct. That you have to do it. But when the flow is not stationary, also the concept of turbulent fluxes is not well defined. In other words, you have to, like the turbulent flux, U prime, W prime, radius average, or something like that, is not very well defined if the process is not stationary. We apply it even in turbulence and whatnot, in the downburst and whatnot, but this is not very well defined quantity. Just like U star, friction velocity is not properly defined in the case of transient non-stationary events. Anyway, this is now. How about if we look? There are two things from these equations I would like to emphasize now. Thing number one, or process number one, is if we look into vertical direction. If we look into vertical direction, you can see outside. You don't go out, and you're just sucked into the air, into the sky, or you're not. My point is the air is not moving very much in the vertical direction, which means we could say that dw dt is zero, accelerations in the vertical direction zero. Viscosity is generally always neglected, but you have to include turbulence. But viscosity is generally neglected, so we end up with this equation. And this is probably the backbone of atmospheric sciences. This is known as hydrostatic equation. Hydrostatic equation basically means that gravity that is pushing the air down is counterbalanced by the pressure gradient force in vertical direction. So I told you that in vertical direction, there is less and less molecules with height. So here is height. Here was, you remember, density. and density was exponentially decreasing with height. Well, the same is with pressure. Pressure is exponentially decreasing with height. Because pressure is decreasing with height, there is pressure gradient force that wants to push air up. But there is gravity that is pushing it down, and the air is just happy the way it is. So that's the pressure gradient, the hydrostatic equation, okay? And this equation works for both air and water. So you can go into the ocean, this equation also works. Now, how about, so that's about wind in the vertical direction. On average, there is no wind in the vertical direction, on average. We will see after the break when that is not the case, when we do have some motion in the vertical direction. And the other wind that is of importance is the wind that is balanced between the pressure gradient force and the Coriolis force. So we say these two forces are in balance, let's say in the u direction. That would mean that there is no acceleration. This is 0, is equal to negative 1 over rho delta p delta x plus f times v. This wind is known as geostrophic wind. Okay? That is wind that blows when there is clearly balance between these two fundamental forces in the atmospheric science. And then the same, you can work it out on your own for V, or namely, you will get U component of the geostrophic wind. That means if you have pressure difference, what he talked about, and I have here pressure P, here is P minus 1, lower pressure, and we are in the northern hemisphere, then you can see that the geostrophic wind will be such that the pressure gradient force, as we just discussed, tries to balance the pressures, but the Coriolis force is deviating motion to the right, and you get, in this case, U component of the geostrophic wind. Okay? So, okay. One more thing. So that means if this is the surface of the Earth, here is height, then let's say here you have this U component of the geostrophic wind. Now, in principle, if you study pure atmospheric sciences, then you would see that geostrophic wind can change with height. These are called baroclinic atmospheres. But generally, when you teach basic course, you say that geostrophic wind is constant with height. But what do you think? Is it constant all the way to the Earth's surface? First of all, it has to be 0 at the surface. Surface is no strict condition. So what do you think? How does the wind change close to the surface? It's decreasing with height. Usually like this. So you start from 0 at the surface, you reach geostrophic wind at a certain height. In the next 1 hour, I'll tell you that height. And then between that characteristic height, atmospheric boundary layer height, namely, and the surface, you have change of the wind, like so. And that change of the wind is generally logarithmic. So if it is very windy at the surface, rest assured it's even more windy up in the atmosphere, okay? In fact, it's windy at the surface because winds at high elevations are high. These winds, geostrophic wind, is driving wind at the surface, not the other way around, because the surface is the sink of momentum. So if there is wind at the surface, it's driven at the part of the atmosphere that is much above your head, okay? So that's how wind blows in the atmosphere. And the last thing, I know I'm 5 minutes over time, just if you look into this equation that you wrote, nobody knows how to solve these equations, but yet there is only 2 forces that can make air move. In the vertical direction is gravity. In the horizontal direction, the only force that can make air move is the pressure gradient force. The other forces are only responsive. They happen once you have motion, okay? So that's about wind and basic dynamics. No extreme winds, nothing, just how wind is generated in the atmosphere. It's generated by the pressure difference. And we'll see in the next 1 hour what is causing those pressure differences in thermodynamics. Okay? Any questions here or online?
We can see the right part of the board. Can you rewrite the equation for the Coriolis force term, like the F equals Z minus something?
So, can you see here?
Yeah, I can see the center part of the board, but not like to the super right where it has the equation.
Oh, here, you cannot see here. Ah.
Yeah.
Ah, this term, okay, F, Coriolis parameter. 2 omega sine phi. Phi is latitude, make sure you use radians, if you are coding this. And omega is angular velocity of the Earth. 2 pi over 24 hours. Right, make sure you put it in seconds. Is that what you asked?
Yeah. Thanks.
Yes. I can also rotate camera, so you see the percentages of the elements in the air.
Thank you.
But I'm not going to use that small board. Maybe it's better to have it like this. Okay, we have break. Switch off the microphone. Okay, recording is back. Was the first hour too simple, too difficult, or too confusing? Refreshing, that's the best answer. Okay, that means this is not difficult to you. So that was a little bit about wind, and not really wind, about dynamics of the atmosphere. And but we also have thermodynamics of the atmosphere, which is very important. And that is, of course, described through first principle of thermodynamics. So dQ is some amount of heat that is supplied to the system or taken from the system. Cp is specific heat at constant pressure, I think 1004 joules per kilogram per Kelvin. T is temperature, P is pressure, alpha is 1 over density, 1 over rho, called specific density. Specific volume. So that's the first principle of thermodynamics. But before we discuss this first principle of thermodynamics, I would like to again go back to the concept of the atmosphere. Here is the Earth's surface. Here is the height, Z. We saw that pressure and density were exponentially decreasing with height. I didn't demonstrate to you it's exponentially, but just trust me, it's exponentially. That is very simple to demonstrate mathematically, but there is no need to do it. But how about temperature now? How about temperature? What do you think? Actually, yeah. How would temperature change with time? Yes. But it's more complicated. It first decreases with time. You see, pressure and density, they're just decreasing. So, if this is also temperature axis, so to speak, x-axis. So x-axis is temperature, y-axis is height. So as she said, temperature from some surface value is generally decreasing with height. But it's more complicated. Only up to approximately first 10 kilometers in mid-latitudes. So this is approximately 10, 11 kilometers above the surface. Okay? So units are kilometers. And then temperature is a little bit constant with height or so, and then it is increasing with height. Here at the mark of 10, 11 kilometers, temperature is a minus 55 or so. And you see that when you fly, because you fly at approximately 12 kilometers, when you look monitor in front of you, it usually gives you temperature outside. You will see you will freeze to death over there. So negative 50 something, okay? And then temperature is increasing up to certain height, 50 kilometers or so. And then it's constant, and then it's again decreasing and so on. We don't have. This part of the atmosphere where temperature is decreasing with height is called the troposphere. And then the next part of the atmosphere where temperature is increasing with height is stratosphere. And these two regions are separated by tropopause. Okay, so tropopause is about 10, 11, 12 kilometers above the surface, characterized by constant temperature with height, stratosphere temperature increasing, troposphere temperature decreasing. What do you think? Why is temperature decreasing with the height here in the troposphere where we live? So you are on that airplane, and there's some old granny sitting next to you and says, "What are you studying?" You say, "I'm doing PhD. I'm going to become doctor of science." And she says, "Okay, why is it negative 55 outside?" And you say, "Well, actually, I'm doing structural engineering." Go and ask some meteorologists. So, what do you think? Why is temperature decreasing with height? It's not easy, huh?
It's related to the emission of the electromagnetic waves from the Earth's surface.
Not quite. That dominates during the night. Yes, that happens during the day as well. But during the day, you have sun, solar radiation. So what you're saying is Earth is cooling down, emitting electromagnetic radiation in the infrared part of the spectrum. And that's true. And that is happening 24 hours. But during the day, there is sun. That is the key to answer this question. So you see, maybe some people think, I don't know, that atmosphere is warmed by the sun. That's not the case. Air that we discussed is actually not very good at absorbing solar radiation. About out of 100% of solar radiation that reaches top of the atmosphere, about 51% goes to the Earth's surface, 30% gets reflected. And then Earth's surface is heating the atmosphere, okay? So the atmosphere is not heated by the sun. But if you get this question and you say, here it's warmer because it's closer to the sun, there is very good chance you fail. It has nothing to do with the distance from the sun. I mean, you're not going to fail, I'm kidding. But atmosphere is predominantly heated from the surface. So the sun heats the surface heats the atmosphere. And then clearly, the further you are from the surface, the colder it gets. Just like if you put your hand next to the stove, well, it's warmer than if you remove it further away. Now, how is this process happening of heating? Actually, first it is happening through conduction, jiggling of atoms, and then after that it is happening through convection. That we will discuss. Okay, for engineering, they also call it call it convection. Sorry, yeah. But I'll talk about convection. Is that clear what I just said? But now the question is, why is it warm here? Why is it increasing the height in the stratosphere? Why? Because it's even further from the surface. Now, you either know the answer or you don't know the answer. You cannot use this one, you cannot kind of figure out, you know.
Because of the zone.
Yes, because there is ozone layer over here, so you got out, you don't get cancer. There is ozone layer absorbing ultraviolet radiation, and absorption radiation increases temperature. So maximum of the ozone is about 20-25 kilometers above the surface. So this is where the temperature is therefore increasing in the height. And then again, there is no more ozone, you're far away from the surface, temperature is decreasing in height again. All weather that is of importance for us creatures on the surface is in the troposphere. So we're not going to look into stratosphere in a whole. This is called the mesosphere, by the way. Over here, and then there is thermosphere above and so on. Okay, is that clear? And generally, temperature is decreasing about 6.5 degrees Celsius per each kilometer. Height. Okay, so now let's go to that concept of convection. Here is the surface of the Earth. What we discussed is that the sun is heating the surface, and that surface is heating the atmosphere. And first, as you know, convection can only occur in fluids and gases, in fluids, in gases and liquids. So the communication, or rather transfer of heat between the surface and the atmosphere cannot be convection. It has to be conduction. So very close to the surface, millimeters and centimeters above the surface, you have conduction. And then convection can take place in the atmosphere, okay? Now, this is what I was about to say a few minutes earlier. There is a difference in atmospheric sciences, what we call convection and what engineers call convection. In atmospheric sciences, convection means parcel of air is moving vertically up, okay? Whereas in engineering, in fluid mechanics, they call convection additive. If there is, so this is convection, at least in our terminology. If this is moving horizontally, this is called advection. Again, in engineering, if you say advection, it doesn't mean, I don't know what you're talking about, because they call convection everything, okay, as a process. But this is what we call advection, horizontal motion, convection, vertical motion, okay? Now the question is, you see, if everything is equally heated, why would this parcel of air go up? How does that work? Well, the answer is everything is not equally heated. Different surfaces have different properties. Some surfaces, like asphalt, absorb a lot of radiation. So they get warmer than the adjacent surface that is some bright surface, I don't know, some white building that doesn't absorb that much radiation. So there are temperature differences, and then the surface that is warmer heats more air above it than the adjacent surface, and you have temperature differences, okay? And these temperature differences cause both horizontal and vertical motion. So you saw that pressure gradient force. What is causing pressure gradients? Pressure gradients are caused by temperature differences. And temperature differences are caused by uneven, usually heating, not only heating, but many other things. But basically, on a big scale, we can just talk about uneven heating associated with different physical properties on the surface. Any questions? Okay. So now I would like to discuss this convection, because that's what is causing clouds for. Okay? So we will define the concept of buoyancy force. So there is a parcel of air over here. Somewhere down is the surface. We will assume that this parcel of air has density rho p, rho of the parcel of air, and there is the rest of the atmosphere that has density rho a. The principle is actually called ambient density, but you can also say just density of the atmosphere. And now this is vertical direction z. What are the forces that are acting on this parcel of air? Well, down is gravity, up is pressure gradient force in the z direction, right? So we can write that dW dt is equal pressure gradient force in the vertical direction, -1 over which rho? Rho p or rho a? This is also pressure gradient force is -1 over rho delta p delta z. But now the question is which rho goes here? Rho of the parcel of air or rho of the ambient air? Rho of the parcel of air. Okay, you're writing pressure gradient force of this parcel of air. Okay, and minus g. Now, very important assumption is that pressure here and pressure here are the same. So the only contributing factor for the pressure gradient force is density difference, not pressure difference. Is this correct? Never exactly correct. Well, it's differences in pressures are usually smaller than differences in density. Okay. So that means that this delta P delta Z I can replace from that greatest equation that we derived, hydrostatic equation. Right? If you go back in your notes, you will see hydrostatic equation that is derived. So we get del dW dt is equal negative rho atmosphere or ambient rho p times g minus g. But it's not minus because this minus and this minus will cancel, so you will end up actually positive over here. Okay? And finally, you get the dW dt is equal rho p rho a minus rho p times g. This over here is known as buoyancy force. So we would say dW dt is equal B. And B is this over here. Okay? So what is buoyancy force? It's just combination of pressure gradient force in the vertical direction and gravity. In the previous 1 hour, we said that atmosphere is static if there is no buoyancy. That means these densities are the same, and the atmosphere, the air is not going up or down. If density of the ambient air is larger than the density of the parcel is pushed up. Buoyancy is positive, vertical acceleration is positive, and vice versa, not vice versa, yes, and negative when this is not the case. Okay. That's why in the car, when you turn on AC, you should always point it up, because that air is cold and heavy and it will sink naturally. But when you turn on board heating, you should always point it to your feet because that air will go up naturally because of buoyancy. So positive, so now I think it's clear that positive buoyancy results in formation of clouds. The air that is going up another important concept. There are many these fundamental concepts that we need to be able to talk about storms in the next lectures. You see, I take this parcel of air, this size, close to the surface, and I go 3.7 kilometers, I don't know, above the surface. I bring this parcel of air over here. This will be the volume. It will increase in size. Why is that the case? If you take balloon, and that, of course, these helium balloons that meteorologists are releasing, they are, I don't know if you ever saw them with your own eye, but they are this big. But if you could see them at 10 kilometers, they are not size of this room, but maybe 5 meters in diameter. Okay? So volume of parcel of air is increasing as the air is going up. Why is that? That's because pressure is decreasing with height. Okay? Pressure is decreasing with height, and therefore this parcel of air is adjusting to ambient pressure. But what is going to happen with the temperature? Is it going to stay the same or is it going to decrease in this parcel? It's going to decrease. Why would it decrease? It's going to decrease because you see, when this parcel of air is expanding, when this parcel of air is expanding, it is doing work on the rest of the atmosphere. In other words, it has to make space for itself. These particles of air need to push other particles of air to expand. And there is no free lunch. So it has to do work. And to do work, you have to expend energy. And that energy is kinetic energy. And that means you are dropping in temperature. Okay? Because you know that temperature is 3/2 K, K is Boltzmann constant, average of, this is from kinetic theory of gases, this is temperature, average kinetic energy of a gas, and then there is some Boltzmann constant, whatnot. So temperature is decreasing, you don't need to know that, but you need to know the temperature is decreasing with the height for these reasons, okay? Now, I don't know if there is any color, anyway. Let's say there were these X's, which are water vapor in the parcel of air. So as the temperature is decreasing, what will happen with water vapor? Well, at a certain temperature, it will condense, right? As you are increasing temperature, you start having condensation. So at a certain temperature, you will have condensation, and that's clouds. That's what we see with our eyes as clouds, okay? So the point is, here is the surface of the Earth, here is a parcel of air. This parcel of air is rising because it's positively buoyant, what we discussed. It has buoyancy that is positive. And it is expanding. And it is expanding even more. And at some point, you get a cloud. It's just parcel of air that kept. So you see also why the bottom of the cloud is pretty well defined. Because it's pretty well defined because this, I don't know now the height, but at this height, temperature is low enough for condensation to occur. And that's the cloud base. And this is the rest. So where is the top of the cloud? Well, this parcel of air reached only a certain height. And then that's the top of the cloud, okay? As we will see in later lectures, when the cloud is very deep, then that cloud has much more potential to be thunderstorm, create severe weather, and so on. These small clouds, like you have outside maybe now, they do not create any severe weather. But very deep clouds can create a lot of severe weather. Okay? And this concept is clear. Now, there is last thing to talk about is the concept of atmospheric stability. So atmosphere can be stable, unstable, and neutral. Let's start with stable, okay? Here is the surface of the Earth. I take a parcel of air and I displace it vertically. You displace it vertically one way or another. If the atmosphere is stable, this parcel of air that is now here will tend to go back to the location from which it came. Now, of course, you know, it will never just go here and stop. It will oscillate now around this equilibrium value, and either through viscosity or turbulence, it will eventually end up being here. But it's not going to just return, it's going to go like this. Okay? These oscillations are known as Brundtland-Sala oscillations, but not so important. This is stable atmosphere. You displace parcel of air, it tends to come to the height from which it came. Unstable, you take parcel of air, you displace it vertically, it actually tends to go on its own even more. It will never come back to the location from which you displaced it. Okay? That's the unstable atmosphere. And we will see now how we can quantify it through temperature gradients. And lastly, of course, neutral is you take this parcel of air, you displace it here, well, it just stays there. So, what do you think? Which one of these which of these three atmospheres is more favorable for clouds and cloud development? Unstable is more favorable for cloud development. That's not always the case. There are some subtleties, but everything else being equal, it's unstable atmosphere that is usually associated with cloud formation. Now, let's say this is how temperature is changing with height in the atmosphere on average, okay? And you have a parcel of air, and you displace that parcel of air vertically, and the temperature in the parcel of air is changing like so. This is temperature in the parcel of air as a function of height. This is temperature in the atmosphere as a function of height. Okay? So they start from the same temperature. This is static atmosphere. That would be like you take a balloon and you attach a thermometer to the balloon and it will measure this. Okay? This is you take parcel of air and you start moving that parcel of air in the atmosphere. Like you hook it for a helicopter, I don't know. So you get, is this atmosphere stable, unstable, or neutral? Stable? Let's see. You pick any height. At this height, temperature of the parcel of air is such, ambient temperature is such. Temperature of the parcel of air is lower than temperature of the ambient atmosphere. It was right, this is stable atmosphere. Okay? Makes sense? But if the temperature of the parcel of air was changing like that, T of the parcel prime, T of the parcel second as a function of height, this would now be unstable, right? Because I take this one, T of the parcel second is larger than T of the atmosphere, this parcel of air will continue going up. And if these two are exactly on top of each other, that's neutral. Make sense? Now, everything that we're talking about here is if the air is dry and there is no condensation. But what happens if you have condensation? Is condensation releasing heat or taking heat from the environment? Releasing. So if this was change of temperature in height in dry parts of the air, and by dry I mean not necessarily there is no parts, there is no water in this case, but water being condensed. Let's say now at this height, some height Z reference, if we go, condensation happens. How is this curve going to change? Is it going to continue like that, or we need to adjust it? And do we need to adjust it like so or like so? If condensation took place, knowing what he said, that condensation releases heat.
Yes.
This. So this, for those of you online, we are assuming that this is where condensation took place. So this is how the temperature will start changing in height. Okay? Namely, the gradient is adjusted, temperature is not dropping with height as much as it was when there was no condensation. And then eventually this will even cut the environmental atmosphere. So this will be the top of the cloud, basically. Cloud doesn't go up. Because everything above now, the particle air is warmer. After this, yes. Do you see what will happen after this? After this, the parcel of air will just continue going on its own. Because here, you have to push it. You have to, one way or another, push parcel of air. It's still in the stable case. But now, when it passes this, now it can go on its own without you pushing. Okay? So you can see the point of this is if you have unsaturated parcel of air that is in the stable condition, you can perhaps make it unstable if you have condensation. Because condensation releases so much heat that at some point this parcel of air becomes warmer than the atmosphere and it just goes up on its own. This clear? So because this can be sometimes confusing. So air is moving up and it is cooling. If there is no condensation, it is cooling more than if there is condensation, because condensation releases heat. I forgot now, but I think latent heat of condensation is 2,500,000 joules per kilogram. A lot, huge amount. Water, as you know, can store a lot of energy. It also has high heat capacity. But to evaporate 1 kilogram of water, and you know that because you go to take a swim, it's plus 30 outside. You are very warm, you go into the ocean, you come out, it's cold. Why are you cold? It's plus 30, ocean is hot. You're cold because you have water on your skin. And that water is evaporating. And evaporation takes energy. And that energy is coming from who? From you, from your skin. So you feel cold. Now, you don't have 1 kilogram of water in your skin. Maybe you have 100 grams. So you have 10%, you give 10% of this energy from your body to evaporate that water. And you know, after 2 minutes, water evaporated, now you're not cold. Okay? Is this clear? Now, we can actually quantify, and that's what we will do in the last 10 minutes. We can quantify some of these stability and instability concepts, okay? And to do that, we will use the first principle of thermodynamics. So, oops. So yes, you saw first principle of thermodynamics, dq is Cp dt minus alpha dp. This is increase of internal energy, this is work done by the gas or being done on the gas. Now, there are two concepts in thermodynamics. Two processes. There is adiabatic process and diabatic process. Okay? So you have a partial pair. How many times you heard this? You have a partial pair. What would be adiabatic process? Adiabatic, because dq, you know from thermodynamics, it's energy that is either supplied to a system or system is giving to something, to outside. Adiabatic means this partial pair is not getting any energy from outside and is not giving any energy. For example, what could be an example of something that is not adiabatic process? Solar radiation. If there is some solar radiation that is absorbed, that's diabatic process. That's not adiabatic. Okay? Turbulence mixing would be diabatic process. We are neglecting all that, okay? So nothing can come or leave this partial pair. That's adiabatic process. Diabatic processes are very complicated. They are always time dependent, and any law that is time dependent is nasty. So generally, particularly in this course, we are dealing with adiabatic processes. Okay? So if we assume that the process is adiabatic, then that law over there is like so. Right? Because alpha is 1 over rho. And now if we want to see how temperature is changing with height, we divide this with dz. So we get that Cp dt dz is equal 1 over rho dp dz. Okay? This would become minus. So I can just do this, okay? When I'm a student like you, and the professor makes mistake on the blackboard, this is the happiest moments of my life. Every time if I was sick and I see professors struggling on the blackboard, I immediately get cured. That was the best thing ever, particularly if they cannot figure out what's wrong. And you're just sitting there as a student like, ah, this is so good. That will definitely happen to me at some point, but still we are doing good today. Okay? So do you see what I have to do here? Again, that famous equation, I have to substitute that dp dz is minus rho g. Hydrostatic equation. I substitute here, and you get that dt dz is equal, so rho and rho will cancel, and you will get negative g over Cp. Can somebody interpret this for me? What does this mean? What is this? By the way, this G is 9.81, this is 1004. You get that this is approximate, not approximate, yeah, 9.8 degrees Celsius per kilometer. What is this? Based on first principle of thermodynamics, assumption, and then this result. What does the result represent? This result represents you take partial of air again. Here is the surface of the earth. You take partial of air and you lift this partial of air. no condensation. As you are lifting it, this particle of air is not interacting with the environment. It's not radiating energy, it's not absorbing energy, it's not undergoing turbulent mixing. You just took this particle of air, you brought it up, it cooled. It cooled because what we discussed, it had to push air around it to cool down. How much it is going to cool? Minus. It will cool for negative 9.8 degrees Celsius per each kilometer that you bring it up. Okay? So you can just remember 10 is approximately. If there is condensation, is this number going to be smaller or larger? It's going to be smaller because there is some energy that is released during condensation to account for cooling that is happening due to expansion. But there is no fixed number when you have condensation because it depends how much condensation you have. You can have very dry air, but not completely dry, or you can have very moist air that is condensing a lot of water vapor. Okay? Any questions? Is this clear? So I was thinking to talk about potential temperature, but I will skip potential temperature, although that's fundamental thing in the atmospheric sciences. If there is need in one of the next lectures, I will talk about it, okay? But potential temperature is something that we use to gauge atmospheric stability in a much simpler, nothing new, but much simpler way than plotting those profiles, okay? Because when you do it in practical senses, you don't constantly plot these profiles and now you do T reference, blah, blah, blah. There is much better way to do it, but we don't have time. So the last 2 minutes I would like to devote to discussing, because unstable atmosphere is very important for development of clouds and then storms. How does one make atmosphere unstable? What do you think? What are the processes? Again, that Jenny on the airplane asked you, how do you make atmosphere unstable? How do you make air go up? What would you say?
For example, during the day, the atmosphere is not unstable because of the long wave radiation.
During the night?
During the night,
Yes.
of the long wave radiation of the.
So you're saying during the night, atmosphere is not unstable. Yes, that's correct. It's mostly stable. So to oppose then what you said, you make atmosphere unstable by heating the surface. Okay, that's why the atmosphere is mostly unstable in the morning, and as the day is progressing, it's getting, because the sun is heating the surface. Okay. 2, what would be other way to make atmosphere unstable? Advection of warm air at the surface. Is that clear? I mean, there's no heating, but from somewhere else, hot air from Italy comes over Canada. Well, that's unsafe. Okay, you are bringing hot air close to the surface. What would be a third way to do it? Well, advection of cold air. Where? A lot. Before this lecture, I had to check how to spell a lot. I'm clearly not native English speaker, as you can see. So if you bring cold air at high elevations, it will naturally start sinking. As it is sinking, there is compensation of some other air going up. So this is making air. And 3 and 4 is not it's radiating cooling from clouds. Okay, so if you already have some clouds, but we are not going to discuss this one. So clouds are radiating energy just like anything. So they make sometimes air next to them cold, and you have downwards that are sinking down, and then you will have some. Now these downwards are not downward, they're destroying everything. They're just sinking parcels of air that are going down. And this is not so important for our. These are generally. This is called natural convection. There is also forced convection, and then we are finishing. What would be forced convection? How does air go up, even if it doesn't want to go up? This is, it wants to go up. But how does it go up? Topography. You have topography, you have wind, namely advection. Well, it cannot go to the mountain. So it has, so you have, maybe it didn't want to go up, but it had to, there is no other choice. There is choice to go around, but in this course we look at. And the last, and that's the end of the lecture. Here you have cold air, here you have warm air. Let's say warm air is moving towards cold air. Which one is heavier, denser? Cold air. So eventually you will get some, it's called front. We will talk more about fronts in the next lecture. But you get a frontal zone. Now maybe this warm air is pushing this cold air a little bit, but it also goes up against. So this is also what we say forced convection. This is free convection, this is forced convection. Both can create clouds, thunderstorms, particularly this is happening quite often, okay? So with today's lecture, which wasn't about any particular storm, but we at least have some fundamentals about the atmosphere that will help us talk about storms. In the next lecture, we're going to talk about extratropical cyclones, which are the most common type of storms here in mid latitudes, okay? And then hurricanes in the next lecture, and then thunders and so on. Any questions? Any questions online? Okay, so please double check the time when the course is open. I think all lectures start at 3 except one. I cannot tell you now which one, but it's in syllabus, so make sure.
Okay.
Yes, on the 10th, okay, but I will forget it, so. I mean, I know that I will be here on time, but you don't forget it, okay? Nice seeing you, everybody, and looking forward very much to see you in 2 days. Bye-bye.
Thank you.
Thank you. Bye.
Thank you.
Thank you.